Hello everyone. Now we have to discuss Laplace transformation. So here I am providing the concept of Laplace transformation, what I need for the circuit analysis, that's it. So what I need for the circuit analysis, that only I will explain here. Okay. So Laplace transformation is a method of solving linear differential equations. First I would like to read all the sentences, later I will explain that each and every aspect. Laplace transformation has its application in solving the transient behavior of the electrical circuits, as the transient response of an circuit can be described by linear differential equations, right? Then Laplace transformation is also a method which is advantageous because this method automatically takes care of initial conditions without the necessity of determining the general solution. Next, Laplace transformation also provides the direct solution of non-homogeneous solutions. So first, Laplace transformation is a method of solving linear differential equations. So what is the general representation of linear differential equations? We all know that dy by dx plus ax which is equals to b, right? This is the representation of linear differential equations, right? So this linear differential equation can be best explained by the transformation method, that is Laplace transformation method. So Laplace transformation has its application in solving the transient behavior of the circuit. So we can use this transformation method in transient analysis. Of course we have conventional method. By using this transformation, that is Laplace transformation method, we are having very easiest analysis compared to conventional method. Okay, that is, for a conventional method is nothing but time domain analysis, but Laplace transformation is provides S domain, that is frequency domain analysis. So compared to time domain analysis, frequency domain analysis is very easy, as we discussed in phasor representations. You all know that, right? So the transient behavior of the circuit can be easily explained by Laplace transformation technique. Okay, because as the transient response of an circuit can be described by linear differential equations. Next, Laplace transformation is also a method which is advantageous because this method automatically takes care of initial conditions. What is mean by initial conditions? Which is nothing but that is initial value that is the value at instant of switching, right? So it is the value. Initial condition means what? It gives the information regarding what? Initial value, that is the value at instant of switching, that is at t is equals to 0, right? Then we will discuss in detail what are the initial conditions while discussing the concept of transient analysis. Don't worry, we will discuss each and every point. Then Laplace transformation also provides the direct solution of non-homogeneous differential equations. Okay, this is what? Non-homogeneous differential equation, right? What is homogeneous differential equation? dy by dx plus ax which is equals to 0. This is what? Homogeneous differential equation. So for non-homogeneous differential equation, for homogeneous differential equation, we are having different general solution, right? So we are having general solution, that is dy by dx plus ax plus b. Let us say this is 1, let us say this is 2. So dy by dx plus ax, which is equals to 0. This is what? Non-homogeneous differential equation. This is homogeneous differential equation. So for this, what is the general solution for non-homogeneous differential equation? Sorry, general solution. For this homogeneous differential equation, which is equals to what? For non-homogeneous differential equation, we are having complementary function and particular integral, right? For this, we are having only complementary function. That's it. Complementary function. What is pi? This is particular integral, right? So simply, if we have non-homogeneous differential equation, we are having the solution, that is general solution of complementary function and particular integral. But if the differential equation is nothing but homogeneous, then we are having only the general solution, that is complementary function. So if you are doing with what? Time domain analysis, we are doing with complementary function, later particular integral, like that. But if you are dealing with S domain, that is Laplace transformation, we will get simultaneously non-homogeneous differential equation representation as well as homogeneous differential equation representation. That is the fourth point. Laplace transformation also provides the direct solution of non-homogeneous differential equations. So we will discuss in detail when we are going to discuss the concept of transient analysis. Here I am providing what I need for that concept, that only I will provide. Okay, next, Laplace transformation representation. Okay, for example, Laplace transformation of a function is f of t, okay, is defined as, this is purely mathematical approach. This Laplace transformation is nothing but purely mathematical approach. This is mathematical approach. So let us say f of s, right, which is equals to Laplace of f of t. This is the representation, right, which is equals to integral 0 to infinite f of t into e power minus st dt. This is the formula for Laplace transformation. So we are converting t domain to s domain, right? F of is nothing but comes under frequency domain, that is s domain. F of t represents what? Time domain. This is time domain. This is what? S domain. It is frequency domain, right? So simply this Laplace transformation is nothing but what? Let us say this is T domain, this is S domain. So let us have from this we are having Laplace transformation, which is a tool to convert time domain to S domain, right? Where S is what? Transformed variable. This is the transformed variable, right? From T to S. Okay. Simply the operation of Laplace transform of f of t should be equal to f of s, right? Is in the complex frequency domain. Simply the operation, that is the operation of f of t, which is equal to f of s, is in the complex frequency domain. Complex frequency domain, or we can say S domain. Simply we are having time domain as well as frequency domain. Frequency is nothing but what? S domain. So, sir, how can you say that is S domain or frequency domain? Where S is the complex variable, that is complex transformed variable, right? Simply we can say that S, which is equal to sigma plus j omega, where sigma is what? Where sigma is what? Real part of S, omega is nothing but what? Imaginary part of S. That's it. Okay. We can write one important point. In the time function, t represents what? Time, right? In the time function, t represents time. Like that, in the frequency function or domain, S represents what? Frequency. That is inverse of time, right? That's it. It is that reason so that the transformed variable is described as complex frequency, or we can say here complex, yeah, no problem, complex variable frequency. So this is the representation of Laplace transform, right? Then now we have to discuss inverse Laplace transform. What is inverse Laplace transform? Inverse Laplace transform. That is, what is inverse Laplace transform represents? Now we have what? L inverse of f of s, right, which is nothing but what? F of t only, right, which is equals to what? 1 by 2 pi j integral sigma minus j omega to sigma plus j omega. These are the limits from lower to higher, that is f of s e power st ds. That's it. This is the inverse Laplace transform representation. That is, let us say this is s domain, this is t domain. Simply we can convert from s domain to t domain by using what? By using inverse Laplace transformation. So this concept is about what? Laplace transformation. Simply, what is Laplace transformation? Simply, Laplace transformation is a method of solving linear differential equations. Means, in the transient analysis we are going to discuss the behavior of total circuit in the form of linear differential equations. That's why we are dealing with Laplace transformation. So in that, Laplace method is very advantageous because this method automatically takes care of initial conditions, whether the solution is complementary function or addition of complementary function as well as particular integral. Okay, this is about the introduction part of Laplace transformation.